Okay, hello everybody and welcome to Curve Properties Part 3, the final part in this 3-part mini-series, and today we're going to be looking at the second derivative. So again, it should be something quite interesting to look at and how we can use it to be able to work out inflection points and in context work out whether a function is concaving or convexing. So the concavity, which is the nature of a concaving function, and the convexity, which is the nature of a convexing function. So hopefully we know that that's a convex and that's a concave. So the concave, the best way to remember this, the concave actually looks like a cave, and that's something really easy that you're able to determine there. And what I've done is I've wrote up a question on the board: find the regions of concavity and convexity. And we got a cubic here, x to the 3 plus 3x squared plus 18, and I've just roughly drawn it here, haven't really drawn it on a set of axes, just sort of drawn the cubic shape there, and I've checked it using a graphics calculator on my iPhone. So from that we're going to try and know that we have a point somewhere where it changes from the concaving nature, which is here, to the convexing nature, and again we call this a point of inflection. And a really good rule to keep in mind here is that the d squared y over the dx squared, which is the second derivative, when that is equal to 0, that's when the point of inflection will be. So because this is a cubic function, the first derivative will be a quadratic of some sort. I'm just sort of drawing it up here, and then we know the second derivative is going to be a linear expression, because remember, we're decreasing by 1 degree each time. Because think about it, when you're applying the power rule and you're bringing that exponent down the front and then you're subtracting 1 from the exponent, you're always decreasing the highest degree by 1. So again, I'll just show you how to be able to calculate the second derivative for a few functions before we get into this idea and we're able to calculate the regions of concavity and convexity for that cubic there. So, just use up this side of the board for a moment and introduce us to the topic. Okay, so didn't do a really good job there, but that's fine for now. Let's say we have an f of x of x to the 4 plus 3x to the 4 plus 6x plus 2. Okay, so we've got a reasonably long quartic there, and from that we can take the f prime of x and differentiate it. And again, this is just a simple polynomial, and it's got a bunch of terms that are just optimizing the sum rule there. So again, we take the derivative of each term that's added together, and we can add all those derivatives together. And from that we would get 4x to the 3. Again, I take the exponent down from there and multiply it by the coefficient of 1, and then I subtract 1 from the exponent. I then do the same, so 4 times 3 is 12, 12x, and in fact I'll make that to the power of 3, because that'll probably give us a better indicator of what's going on. So it'd be 12x to the 2 there. And then it's plus 6. Because of course, if we just have a number and then an x value, it's just going to be that coefficient when we differentiate it. And the derivative of constant is always 0. Gone through that in many previous videos. Still having trouble with that, I explain it in quite a few, so just check out another video. And then we find the f prime prime of x, and this is the second derivative. So this, again, the first derivative, it helps us find when the derivative is increasing and decreasing. So it helps us find stationary points when it's 0. But again, the second derivative helps us find the inflection points, where it changes from concaving to convexing. And that's when it's equal to 0, as I had up on the board before. So f prime prime of x, we go 12 times 4, 3 times 4, sorry, kind of skipped a step there, but 3 times 4 makes 12, x, and then we reduce the power by 1, so we get 12x squared. Plus, and then it's 2 times 12, which is going to make 24, so we have 24x. And then when we differentiate 6 there, we end up with 0, because again it's a constant. And from that, if we made that equal 0, and we solve for x using a quadratic polyroot sim, for example, or by factorizing, or by using the quadratic equation that you should all be familiar with from previous videos I've done, then we'd be able to find the point of inflection. Okay, so now that we've sort of got this idea of what the point of inflection is, it's where the function's changing, it's no longer a frowny face, it's becoming a smiley face, we can have a go at being able to work out the regions of concavity and convexity. And again, if you need a few more examples of being able to differentiate and find the second derivative, just come up with, say, a polynomial that has a degree greater than, say, 4 or 5 or something, and then just try and differentiate once, and then differentiate your answer again. It's a good thing to get into the habit of, and of course, it's very important to know what they're asking you for, because a point of inflection is very different from a stationary point, unless you have a horizontal inflection, which is also a stationary point, but I won't go there. Okay, so let's go to our question. And first thing we should probably do is take the first and second derivative for this cubic, and from that we'll work out where is it concaving, where is it convexing. So we have our f of x, or our y equals our equation, and that f of x, again just using common notation, is x to the power of 3 plus 3x squared plus 18. And that's going to give us a nice cubic, like what I had up on the board just a moment ago. And then what we do is we take the first derivative. It's going to be 3x squared, again bringing the exponent down into position of the coefficient, and then subtracting 1 from that exponent. Same thing here, 3 times 2 is 6, 6x. And then we differentiate again, and we get 6x, because 2 times 3 is 6x, plus 6. So we get 6x plus 6 as being our final function there. And from that, we're able to work out where this original function is concaving and convexing. So as I said before, the point of inflection, where it changes from concaving to convexing, is when the f prime prime of x, or as I had up before, the second derivative, the f prime prime of x is also another way of denoting the second derivative, when that's equal to 0. So what we have is we have 0 equals 6x plus 6. And what we can see here, and we can even notice it from the diagram I had up before if you just want to rewind the video, you can see there's only really going to be one inflection point in a cubic. And from that, we just solve for this value. So we bring that 6, that positive 6, over to the left-hand side, and because of it, we inverse the operation. And so we get negative 6 equals 6x. Nice and simple. So now what we do is we want to solve for x again, and therefore what we do is we bring 6 to the other side. So we get negative 6, and it's divided by 6 because it's in the numerator on this side, so it's going to be in the denominator on the right-hand side. So we get negative 6 divided by 6, and therefore x is going to be equal to negative 1. Okay, so that gives us an idea of where the horizontal inflection point is. And if we wanted to, we could put this negative 1 back into the formula and actually get a point. However, because we're only specifying it based on an input, because we're only specifying it based on an x value, we really only need to define the regions in terms of x. Because it's asking, okay, so for what input values will we get it concaving, and for what input values will we get it convexing? And it's nice and simple here because we only have one inflection point. But if you did need to calculate the actual point of inflection on the original function, then I may as well do it now because I've got a bit of time, that we do the f prime prime of negative 1, and it equals 6 lots of negative 1 plus 6, so it's negative 6 plus 6, and so we get 0, so it will be at the point negative 1, 0. Okay, so hopefully that gives you a bit of an idea of where the point of inflection on the actual function is. So now, let's see what will actually be happening to the function prior to and after the concaving and convexing nature. And to do this, we can draw a sine diagram. have is we have our point of inflection there, and we want to know whether it will be positive or negative. So, because we have -1 there, what we can do is we can take a value less than -1 and substitute it into our second derivative. So I'll find the f prime prime of -2. And that equals 6 lots of -2 plus 6, which equals -12 plus 6, which equals a -12 plus 6 is going to make -6. So it's going to be negative on the left-hand side of our actual derivative there. And what we get now is we also have the positive side of this, so we can do for the f prime prime of 2, for example, now, because that's larger than it. So it's going to be 12 plus 6, which is going to make 18 this time. So we're going to get a positive value on that side. And now the negative slope is obviously going to be a concaving function, because it forms sort of an upset face. And the concaving function means that this function is going to concave up to the inflection point. And that makes sense based on the cubic that I had on the board before. So just remember, negative eyes, it's sad. Okay, and now what we do is we consider what the positive value means in context of our concavity and convexity question. And positive means that it's going to be happy, so it's convexing. And so we've got our sign diagram there, and we can write a final conclusion. And that conclusion is, and I'll probably write it up here, just so it's just so I have some room. But so for x is less than 1, -1, sorry. X is less than -1, it is concaving. And for x is greater than -1, it is convexing. And there we go, we sort of worked out the concavity and convexity nature of this actual function. So again, it's just using the second derivative, and just make sure you sort of have the idea of, okay, when do I use first derivative, and when do I use second derivative for any video on the curve properties series. Consider whether you're finding what's happening to the slope, whether you want to find a stationary point, or whether you're just sort of thinking, okay, I need the point of inflection. Again, any comments, write them in the comments section. Hopefully this has been okay and has helped you out, but there we have it, curve properties part 3, the second derivative, and hopefully you're able to follow along with it. It's a nice little thing to be able to help us understand more about a function. Thank you.